Okay, so capital N, just think of it as 2 to the n. So you have the standard unit vectors in R to the n, which fix an index L in n, and W is the unit vector which is like just the uniform addition of all the vectors. Okay, so what's the length of W? What is the length of W? 1. And so L is fixed. L is some fixed index. So that is that corresponds to our x. Z. Or yeah, Z. Yeah, which Z. The thing you are trying to find. And and let A be now consider this two-dimensional. The whole point is to consider this two-dimensional space spanned by W. This now because the full superposition, the complete superposition of all the basis vectors and the basis vector EL. So EL will be just what will be the KZ. So right, so there will be a unique. So the picture is. So is this here? So the picture is something like this. So. So now we have the ingredients to map. So almost have to map the previous size to global search. In the notation there. So here is our vector, the vector we are trying to find, which is EL, right? And in this thing here is W, which is I'm going to call it I. We just call it W, but this is the 1 over 210 I going from 0 to n minus 1. So I'm thinking of each bit thing as representing the corresponding integer. There are these many bits. So this is W, and this is A. So that's what this vector A was. So what is A in terms of the other things? One over root n minus 1. I equal from 0 to n minus 1. I not equal to Z. That's what A is. Okay. And this is, yeah, so in that exercise, we call this angle. Yeah, so, so W hat is this thing here. And this angle is theta. And the question is asking is that so let's take any vector u, it's in the plane spanned by so this in this plane, the plane of the drawing. Okay. And what we want to do is to rotate once. So what is this extra notation, right? So this RU, so for any vector u, is the rotation is a reflection in the mirror that is so you take a vector u, take a mirror orthogonal to u, and you reflect in that. That basically amounts to changing the sign of the component in the u direction. So that's what these operations are. But these operations we have been seeing very much, right? Our oracle is the operation. And this thing that we just looked at, I minus 0, 0, that is also like such an operation. But what was this exercise asking for? It was asking for these two operations for the following thing. We wanted to change the so REL, which is just change the sign of the EL component. Do we have that operation available to us in the slower case? Is the rotator. It's exactly the rotator. What about the other one? The other one is it's like so what is it? It's like sort of reflecting in the. So if I look at the picture, so it's the reflection in W hat. So what is it? So what component does it reverse? The reflection in W hat. W hat is perpendicular to W. So reflection in the mirror orthogonal to W hat. So sorry, the mirror parallel to W. So what does it do?
So it is W field. So you mean like that W?
So it changes the
No, like W tilde. Like reflection along what are you referring to?
so yeah, in the exercise it was we don't care too much about the exercise, but so so this was this.
Yeah, so
So let's look at it, what that means geometrically. So geometrically it is changing in so geometrically you know what that means. So that so
this W hat or W tilde that is like orthogonal to W right?
mhm.
So if I reflect along that, that's just like adding a minus sign or something
To what?
to W.
Uh,
Vector will have
to W hat, to the component of W hat.
no, but the entire vector is like it's changing direction right from here to there.
Yes, but so the W hat component is changing in sign.
So we're reflecting like that, right? It is W tilde is like this, and so that would be like that. So one thing, like one component is
Yeah, which component?
so why should it be one component? Shouldn't it be like both component because you're reflecting it along an axis which is orthogonal. So I mean both as in like Z and A, both the components will have negative contribution. So I mean what I'm picturing is basically if I have this image, then this thing will go here. So this component, both.
Yeah,
will be
yeah.
But like the point is not the axis. Even this is we do that as a point that's but so we have to just if we do it with respect to the normal the usual coordinate axis of the coordinate. So we have to take it along with respect to A and something else. So like W is let's say this is so what is the angle? Which is theta. So
But okay, so what was the upshot of the exercise? After these two together did some operation, which was more or less like a rotation. Right? Essentially, it was a rotation, and that rotation depended only upon the angle between W and A. Right? So somehow we have to be able to do this. So the other operation that we are looking for has to be some kind of a reflection along W or W hat, and then this geometric problem told us that each of those it was basically rotating things towards the EL vector by an angle that was just the angle, like twice the angle, like twice. Yeah, so that is so. I mean, it's not so. It's important in the sense that if you do it, if you get the factor wrong, the reversal will fail. So So let's just see. So let's redo this thing. Actually, we'll have to redo again because there's a slight difference between the two, but just for the intuition. So the previous thing was something like this. That one operation, so like take some vector u, which is whatever the state of the circuit is. Like, so the current vector is something like this between product and free. So let us think of it as a angle. So this will be angle phi that it is making. We change, so we first reflect it in the mirror that is parallel to A or orthogonal to Z, right? So so actually it makes more sense to say what is it orthogonal to. So if we do it in the mirror orthogonal to U to Z, then what happens? What happens to phi in this picture?
Yeah, sorry.
It becomes minus, but it just reflects. So because so it goes here. That's the first step. That's what the oracle does. Phi becomes minus phi. Okay. And now, yeah. So this is the tricky thing. So what I would actually have wanted to do is to reflect the W component, which is this one. Okay. So that would be like reflecting here. So I extend this W hat. Yeah, so this I made not an error in Excel, but yeah, it makes things a little bit complicated. So now we want to reflect the whole thing into this thing, like into this mirror. Okay. So what happens now? So yeah. So what happens now? So the angle. So what are the angles, right? So sorry. Right, angle A will be so whatever this angle is, it will add that also. So minus 5, and so whatever this angle is, and this angle is that theta. Right. So this angle is that theta. Because this is theta. This is theta. So basically, in this operation, so R, if I had RW composed with REF, you wrote change so that maps phi to minus phi plus 2 theta.
Yes.
Right?
Phi is going to phi plus two.
Why? No, because this vector will now go here. Right? So it changes by other two.
But two.
Did it makes a lot of okay. Yeah,
Mirror was W tilde, no?
Yeah, mirror was double tilde.
You written here, you said R.
No, yeah, sorry, yeah, my sign convention is gone all haywire. Maybe okay. So given the picture I have drawn, it's actually easier.
The picture you have from the
Picture is correct. It's like just like so. Basically, the issue is this: the unitary operator I did the calculations for is the reflection along W. It does not matter because they all differ by a -1 place. So in the end, all calculations, all the probabilities will be the same for both of them. Just the pictures look much more complicated for what I'm trying to do now. So let me fix this in a different way. So. Um, Yeah, okay, yeah. So let's just do this. So what happened? So where did it go? So the reflection was now happening in the
In Excel to W tilde reflection. W tilde.
in double tilde. So the double tilde component was reversing. Let's see. You can like this is the simplest thing we would handle let me do the calculation that will look the picture will look simple. So suppose I was not doing the rectangle, I was doing this one, the one in the exercise. Okay. This one. Yeah. So then what would have happened? So then what I'm doing is so this theta goes to minus, this pi goes to minus pi. That's the u prime. Now you're reflecting in W. So the angle is minus pi. So it's pi plus theta, and it whole trans goes into the other side. So there is a so the new thing is like so this and this here, where this angle is theta plus pi. This much, but there's another theta here. So in this case, what happens is that pi goes to pi plus 2 theta. So each such reflection rotates you in the direction, in the correct. So if you assume that you started off in the first quadrant, okay, then you rotate by 2 theta towards the correct, towards your answer. Okay, whatever the theta was in this case. Okay, if we were doing reflection in the in W, not W tilde.
You will have a phase difference, right?
Yeah, there's a phase difference, but that will be fine. So okay, let's just we show. Yeah. Okay. Yeah. So this one does a 5 plus 2 theta. So if we do this, right. So we know what theta is. What is theta? This was part of it, right? So sin theta is or maybe sin theta is what? So sin theta is just the inner product of z and w, which is 1 by root n. Angle theta is about 1 by root n. So each time I am moving by 2 theta. So in roughly root n steps, I will be at like very close to Ez. And actually, I have to stop there. Right? Because if I keep moving, if you do the calculation for other angles, it will keep moving, it will keep rotating. So you have to actually stop. So you have to actually get the right value of theta, stop at the right point, but then you can stop quite close because each time moving by this angle 2 theta. So you can come within theta, whatever the value of theta is, and that value of theta is about 1 by root n. So the inner product that you will have at the optimum point will be about 1 by root n. And what the optimum point is also you can compute in a classical computation. So you just have to run the circuit for that many times. And that T is how much? It's pi by 2 by. So okay, so where will you start? You start off from 0. But 0 is not a good starting point. 0 is not even the span. So what should you do then? So you want to start maybe from W if you want to do this. And if you start from W, so but how do you get to W? So that's the first question. Actually, the other question which is how do you get the reflection? So, but let's see. So the algorithm, the sketch so far is something like this. Yeah, sorry about the fiasco with this angle convention. We'll fix that. Yeah. So far the sketch is something like this. Sketch is one start at of course 0 to the end, right? And then somehow convert this to this W, which is 1 by like the full. like all the bit streams. Then apply Oracle followed by yeah. So what I was doing was I was changing the I minus W hat to W hat. Okay. So this we will not do. We will actually try to do I minus W. Then we'll see how we go about it. So it is actually that. So let's
That was what you'd done originally, no?
yeah. What I did in the exercise was I minus W hat W.
But what you did just
No, what I did also in the picture was also that, which is the nicer story. But what we want to do is this, and something very similar will happen here. Same thing, theta rotation. Okay, but the question is how to do this. Okay. So how to do this, and the same 2 theta rotation. And after carefully chosen, T. So it is basically up to like plus minus 1 equal to pi by 2 minus theta divided by theta. Let's throw this into here. Um, Many steps of this, many repetitions. So basically, apply whatever, apply. All of this T time. T is this. Oh yeah, just 3, yeah. See, measure in computational basis. But the point is that at this point, if you believe the 2 theta picture, which I did for some other vector, but if you believe the theta picture, it will have come about theta close to the correct answer. So the closest in theta, at least 2 theta close. And theta was about 1 over 210. So the probability, so the cosine will be about 1 minus that, or whatever so the angle between Ez and your vector will be something like, will be at most 2 theta, actually at most theta if you do properly. So, and the sine of that angle is 1 by n. So the cosine of that angle is actually pretty large. Like it's like 1 minus 1 over n. So with that much probability, like about 1 minus 2 over n, you will get the correct. So that's the goal. But the point is that you have to stop at exactly this t. If you start proceeding, it will become worse. But there are many things remaining. So both 2 and 3 are remaining, and the other things is remaining that also say that this actually works. But I showed you something very different. But let's first do these 2 things because they have roughly the same reason. So how would you get to W? 30?
I would get on all kids.
Yeah, so if you've seen this, so this is like the Fourier transform, which is like it's a classical thing. So you're basically doing the Fourier transform. This is so. Wait a second, I might be able to do something here. Oh no, this Jamboard only allows things in the middle, like not so. Then we just go to search. Yeah. So, just consider the following. So, in step 1, constructing this W. So this what you do is you just have a bunch of zeros. And you put a edge on every one of them. That's it. But what is this? So just look at, so what is edge 0? It is 1 by root 2. 0 plus 1. So this edge tensor to the power n 0 n is 1 by 2 to the n by 2. And then all of these things will be there. Is that? So this is easy. Yeah. So now second step, constructing I minus 2 W. How do we do that? How do we do this? Right.
W bar one.
Right.
It's not one matrix. It's W. W space. I minus space on one matrix.
Yeah, but we have to do it with basic gates. Yeah, it's a very simple matrix, but you have to do it with basic gates, basic 1 or 2 qubit gates.
You already created this unit image in the couple of slides ago.
Which one?
Like,
I did I minus 2 0 0.
yeah.
Yeah.
So instead of 0, we can use U.
How?
I'm sorry, W.
Because we can't start like not really. I mean, the circuit was very special. Like if you use classical gates and all these things to get high minus 2 0. But yeah, you have to use that circuit. So we have to use that circuit. We already have a circuit with analog. Or I minus 2 0 0.
So starting with this instance and
Yes.
so you can pull the instance out to the net. And you write
So okay, so another factor is its own inverse that we need to check.
so you can do H tensor n then I minus 200 H tensor.
Yeah, so that essentially works. So consider nothing. So consider this that so consider HN tensor whatever identity on the ancilla, right? Times that u thing, yeah, times the u times again this tensor and no like tensor and again I consider. Right. So the picture is like this. So it is u. Here are the answers. .
What is the dimension?
Sorry.
What is the dimension of U?
Yeah. So yes. So U is the quality where U is like it acts on. So whatever. So UX tensor 0, whatever the dimension of answer or number of answers is equal to I minus 2, 0, 0. Tensor 0 number answer. This name. And it's also n. So this I claim does the yes it so this implements I minus 2 WW with answers.
So, can you not implement them without answers?
Yeah, as far as I know, I mean, actually, I don't know. So does it? So is it clear? This does it with answers? So let us see it. So U has this property, and we are not putting H hat. Those guys are actually an identity of the answer, so that's fine. So when you put H hat then on both sides identity, so the ancillars anyway are working on their own. Here you get like X squared, but X squared is just identity. So this part remains identity. H 0 to the n becomes W, and H dagger is equal to H inverse. So okay, so now the only thing that is left is to do the geometric calculation, which can be done with algebra or geometry. Let's try to do the geometric thing first. If it fails, we'll try to do the algebra. Hopefully, we will not get to that point. So, yeah. So, we just have to justify the angle. Justify the rotation planes. Actually, let's do the algebraic thing. Maybe just to get a feeling for what that would look like. I'm trying to do it sort of from scratch, so we can do that. So, but let's see. So, what we are trying to do. Each operations, the operation is I minus 2 W times I minus 2 Z. This is the operation. Right. So, yeah. And yes, so this becomes so, and we know that W is equal to this n minus 1 by n a plus 1 by 10. A is equal to 0. This was the picture that you were given. So, same particular W Z is equal to 1 by 10. Which is equal to sign. Okay, so so now what it becomes is this becomes I minus 2 plus 4 by division. And, so this, let me just write this cosine theta here plus sine theta I minus 3 cosine theta. Percent. Cosine times that's it plus 4 sine theta cos theta is plus 4 sine square theta. That's it. Okay. Yeah. So at this point, it should be believable. This will look like a rotation because the point is that we are now actually just looking at two-dimensional matrix, 2 cross 2 matrix, just in the vectors A and Z. Everywhere else is iron. So in this space, we just want to show that it looks like a two-dimensional rotation, right? Yeah. So yeah. So this will be I minus 2. So let's just do so I minus. So what is the AA business? So AA is 2 cosine square theta. That's it. Yeah, yes, that's it. What is the AZ plus AZ? Okay. So AZ is coming from sorry, 2 cos theta. And plus ZA, which is what? No. Yeah, minus 2 sine the cos theta. And then there is a ZZ. Which is minus 2 plus 2 sine square theta. Okay. Minus 2 plus sine square theta. Okay. Yeah. Okay. So this whole thing now looks like yeah. So there's the identity. So in the AZ basis identity plus so let's say A is this, Z is this. So it's minus 2 cosine square theta. 2 cosine sine 2 theta, because the 2 sine theta cosine theta, the minus sine 2 theta, and here it was minus 2 plus 2 sine square theta. And now we're there. So this is like 1 minus 2 cosine square theta, sine 2 theta, minus sine 2 theta, sine square theta minus 1. And the point that cosine 2 theta is equal to 1 minus 2 sine square theta. Right, which is also equal to 2 cosine square theta minus 1. Okay. So this is negative of cos 2 theta minus sine 2 theta. Sine 2 theta minus the cosine 2 theta. So it's up to minus 1, so a phase of minus 1, it is rotating by 2 in the AZ plane. But the phase doesn't matter because in the final, so you can just remove the minus ones added at the end because the no projections, like in the end, all you care about is the magnitude of the projection, and that is phase of minus 1 will not change. So this is the other one, the one that I was doing in the thing, will be actually a rotation by there will be no phase. That's only. Yeah. So this one would like rotate and then reflect. So rotate by 2 theta and then reflecting the origin, again pointed. So that's what the one is saying. But that reflection you can just ignore. So there are many like the physical way to see the phase will not matter because in the end, like it's multiplying on thing. The algebraic way to say is that so you have this matrices, but each of them has some sign, but the sign is community mirror. It comes at the end. So yeah, so that's so it is a which up to a global phase. Is a rotation by 2 theta. So we saw it both by one nice picture, one pretty messy picture, and algebra that's the 2 theta pictures. Okay, so this concludes the Grover search. So there are there are some interesting features. One is that it's weird for a search algorithm that you have to know exactly when to stop. If you don't stop there, you can just continue, and you will not even know that you fall. The other thing is that this was here you knew that there is only one answer. If there are more answers, it will fail because again, if you can do the analysis again, the number of steps that you run the algorithm depends upon how many correct answers you have. So it's the same kind of algorithm. So this 2 theta picture will still be there, more or less, but the angle theta will be different. So that will depend upon how many correct answers there are. Here it was just one correct answer, there was 1 by root m. There it becomes something like n. Something there. So it's like root m by something like that. So, but it's an easy calculation. And so the steps will depend upon how many answers. You have to know also how many answers are there. So there is work on trying to fix these kind of things. But yeah, so but there are these two somewhat weird features that Grover search has for a search algorithm.
So if there are more answers, the variants of the algorithm?
No, the algorithm will work as long as you know how many.
I see, exactly.
Yeah, but yes, but people have worked with things where you try to find out also how many. Yeah. But yeah, this same algorithm, same analysis, you just will change the modulus and value of theta will work for the case when you have more answers, as long as you know what to do. I mean, the analysis doesn't need to know, but yeah, in the end, when you stop, you will need to know how many answers there. So the calculation of the number t, how many steps t.
So in this entire algorithm, I don't understand where are we using ANSYS last day? Where are they getting experience?
Yeah, so actually, so where did we use that first? So that's a good question. So I can see that. So there are only 2 kinds of quantum operations going on here. One is Hadamard in the beginning to convert 0 to W. That is nice. So time theta, and so there is no answer. What's the next one? Measurement operators. That we have available. But in principle, that oracle itself would be answers potentially its own. Right? So that is also there. But we are assuming that. So actually, when you start doing this, so this is an oracle, right? But the oracle could be doing some weird thing also, like so this is an assumption that the oracle was doing nothing, right? So the oracle had these input bits, and then it was just passing them out to you. The oracle could potentially have some other qubits of its own, where it could try to store things and potentially try to cheat with you based on that. So these kind of things are important when like dealing with so-called Google verifier kind of protocols. Here, because we are in the oracle is honest, it doesn't make sense. But but this is an answer. The oracle is not doing anything else. If it has any qubits, they are not entangled with what is happening in the rest of the earth. Then it goes, and then we have to do our version of the oracle, which is this oracle for W. That required answers. Right? Because that required this I minus 200, and the only construction we had was this based on classical, which required at least one answer, actually more probably, because just the classical construction itself requires some space. And so that those are all there for the answer.
But in the classical circuit also,
Yeah.
we are using like CF followed by Z.
Yeah.
And CF is only working on like finally I'm working with X and 0, right?
No, but CF itself would require answers. And then
So it's like it may or may not require. That's not a
yeah, so actually I think it does. But the point is, even if it does not, still you need one answer to use an output of C. So remember, how did we get to this U? Yeah. So at least one answer I think.
at least one.
I think CF also needs it, but I have not checked. I mean, well, usually it's hard to prove that something needs space. But yeah, like at that level of granularity, it needs one. I think in this case it should require. But yeah, but there exist classical problems where space is needed. More space than can be than so the input space is not there is more space needed than that. So such problem is natural problem. Okay, so
Last part, we were just like, we were trying to justify that this thing indeed has rotation.
yeah. Well, we were proving it again. So for the index side, I've done something else. There's a reflection in a different thing, orthogonal. And this was just saying that what the algorithm itself is doing that rotation, followed by a reflection in the origin. But reflection in the origin doesn't count because it's just a change in global space.
So for this rotation, we're getting 2 theta, right?
Yeah, there was zero.
But you made a comment a couple of minutes ago that it's possible that you can do it in theta, like not 2 theta.
You can get within theta by.
No. That's a question of how close can you get to the point, right? So each time you're rotating by 2 theta. So you start at theta,
Yeah.
and this is some irrational multiple of 2 pi, right? So the thing is, you have to move pi minus theta, pi by 2 minus theta, divide by 2 theta. That's the number of steps. So, and if it is a closest integer, you should be theta closer, right? So like you're moving in intervals of 2 theta, right?
Right.
So the closest one will be theta close typically, because if it is more, if the previous one is more than theta close, when I move, the next one will be less than theta. So that's all. Okay. So you can come. So that when you stop after that many steps, you can choose the number of steps, providing a theta quite accurately, so that when you stop, your the angle that you make with the correct answer will be at most. Yeah, so that was the basic thing, that if you're moving in steps of t, then and you're trying to hit an integer, the closest point will be about actually 2t by 2. Like they're moving in 1 meter in steps.
So if you want to get like arbitrarily close, you have to change theta, right?
Yeah, you can't change theta. So this is it. The algorithm has this cognitive differences.
So
If you want more,
lesser number of like
so one thing you can do is so there's nothing in the algorithm to do, like you can run the algorithm again, the whole thing again, like just repeat the whole thing again. So and each time there is probability of success. So that we can amplify your problem.
but if sine theta is proportional to 1 by root n,
Yeah.
then for
But n is pretty big.
n has to be big.
You know, it's pretty big. It's like
But this algorithm won't perform very well for small n's, then, right?
But why would you need to do anything to small n?
Now this is like
Yeah, if capital N is like 4, then just look at 4.
yeah.
Yes, so yeah, sorry, but this is one of these things about complexity. You only worry about large, small levels. You can do first before you go. Yeah. But even there, right? I mean, like even there, it's not completely trivial. Like as like n will be at least two, right? The probability success is half. You run it like 10 times now. It's suddenly one minus one by 3 times. 99%, like, more than 99%. Okay, so any more questions? So if not, then okay, so we can break it for now and we'll start with phase estimation. At 355.
So those are how they stumble on.
I don't know. So I heard
Come on.
So let's start with the phase estimation. So at a high level, with a high level problem, is access to a unitary U. And this is more like a classical description. So we have to make copies of it. Important data. And eigenstate. Alpha of U. That you yeah, I think that so why can I think that? Just use unity, just eigenvalues are all on the unit level. So it has, so how do we have eigenstate access? So this access, this is on some qubits. So there are certain qubits which have been prepared in this state. So like as a quantum state. So we have access to the classical description of the circuit, which gives to applying variance. And in this alpha we have access to as a quantum state. And the code estimate the high level code is to estimate is like the same thing, estimate the eigenvalue. So that's the simple. So initially we just try to get some estimate of theta. Like so of course what the trivial estimate of theta is between 0 and 2 pi. So initially we just try to get something better than that. Okay, so let's say up to something like pi by 8. That's the first step, and then we'll see how to improve upon it. Okay, but is the question here? So we are somehow we have it's not like unlike Oracle here, where it's just given to us, we can just put it there. We can in principle play around with it, change things inside this what it will say white box, access. Right? And that's okay. The identity is given on one. So there's one copy of the identity given. One. So no copies. There are no copies. This one. Right now there are no copies. It's in many of the applications it won't matter so much, but here it's. So this is the situation. So far we have always been talking about the material and so on. So it almost looks like how can you measure it? But this is slightly different because it's what an operator is doing on to one particular vector. So there might be hopes. So any so any kind of suggestions, like maybe not even as a goal as a circuits, but maybe if you could control you can we do something. So we have the white box access. So let's say so in particular,
Does theta have any relation with alpha?
no, alpha is you don't even can read it, right? It's just given to you as a state. So you don't it's not no description of alpha is given to you. There are certain qubits and you're told that these qubits are the state. So in particular, let's say we assume. For now, we can. But later on, we'll have even more assumptions. Assume that we can do control W. Control U. So now, given that we can do control U, is there a yes? Do you have some?
So theta can be any arbitrary case.
Huh?
Like theta can be any
Yeah,
arbitrary.
yeah, it's no arbitrary case. We want to do something where if you measure it, we see like something that depends on it. Right? So, and we can do control you.
Any one answer of
Well, yeah, whichever to control the U, and on that you do something. So let's look at the obvious circuit, right? And see what could happen. So obviously, kind of thing because we have control U. Let's see what a control U will do, right? So of course the idea would be to feed the alpha into this, right? Something else. So then and then depending upon the control state, whatever. So given all that we've been doing, what's a natural thing to do on the control? Yeah. Yeah. So you put a see this what happens. Okay. So you put a header mod on this, what happens? So then the 0 to alpha is mapped to 1 by root 2 0 alpha plus 1 x I alpha 1. Okay. Is that correct? Yeah. Okay. So far so good. But now suppose now we say, oh, that's good. Only one of them has a factor. Alpha is there, right? So this I can even write it as 1 over root 2. So this is another nice thing. Plus x of I theta 1 tensor alpha. So if I do any measurement on just this qubit on the top, alpha will remain there without completely like unmodified to be used again for example, right? So, but what kind of measurement can we do on this? If we can we do in the so if we do in the computational phase, what will happen? We're probably half. There's no difference on alpha, right? So what should we do? Yeah. Okay. Very in doubt to alpha. So whatever, that's not good. It's not good, but yeah. But it makes sense. The point is that now there will be some this angle will not show up, and yeah. So okay. So this maps to what now? So alpha part remains just there. Alpha part will be acting on this cube. So this becomes what? So this becomes half 0 so plus 1 by root 2 plus x for I theta by 0 minus 1. So, okay, so yeah, so we're trying to do phase estimation for U and alpha is the eigenstate, and here is a candidate circuit right, with the Hadamard problem. So you can see what happens. So 0 alpha maps to this circuit, and now let's see what this is. So again, we want to do all the measurements in the class in the computational basis. So let's just write it in terms of the computation. There's 1 over root 2. Sorry, so this 1 over 2. 1 over 2. And there is a 0. And 0 has a 1 plus x of I theta. So what we know is that U alpha is equal to x of I theta. Our goal is to estimate this. Plus 1. 1 minus x.
Then what are we given? We are given U.
Yeah, so U we are given a classical description of, so we can even do some arbitrary stuff. For example, we can do control U also. And this alpha we are given as a quantum state.
We are promised it's an eigenvector.
It's an eigenvector. So right now I'm saying alpha we are promised it's an eigenvector. with eigenvalue TPI.
Given it as a state, on the wires you have.
On the wires, yeah. You have more access. You have given a classical description. You can put, for example, you can do control U. So this will be so to always keep the factor in limit. So U there was some classical computation, was really just multiplying by 8. So that we could estimate. We could do whatever. We could write a circuit for it, a classical circuit for it even. There was so circuit to control version of that. Everything. Alpha was some quantum state, so that we will have given to us on the ones. And so we want to preserve alpha also. In the end, we want to preserve alpha, and we want to get some. So at this point, after doing this circuit, we just Hadamard, control U Hadamard, we are in this state. The alpha is tensor. If we measure on the top qubit, alpha will not be changed at all. So that is good. But what are the probabilities? So earlier the problem was if we had done only one Hadamard, you were here, right? And here, so this is this. So if this Hadamard, the second Hadamard is not there, then we will just be here. And this we saw okay, because if you measure, we just get 0 and 1 with the same probability. Theta doesn't show. Now does it show? Yes, now it does show it. And so what is the probability now? So what is the probability of measuring 0? So if we measure the top bit, so this is the notation often used for this. Like this measure, but people use it like CSS standards. But anyway, so if we measure the top bit, the probability of 0 is how much? Is the length of this 1 plus x for I theta squared by n by 2 squared. Okay. So how much is that? So you can do it geometrically also. The picture is like this, right? So or you can just do trigonometry, whichever is faster. Picture that you have one. This is the e to the I theta number. Right, this is angle theta, and the length you're trying to measure is the length of this perpendicular. So it's a isosceles triangle, side length 1, vertex angle theta, and you're trying to get the length of the perpendicular. So that what is that? So that is just it's like cosine theta by 2, right? Yeah, we just rotate it like this. So it's like cos square theta by 2. Right? Which is also 1 plus theta by. So at least some correlation, right? So if I do, but okay, still not so much, right? So what is going to happen? We are going to do this, we are going to get 0. We don't just get 1, 0 or 1, but we know that the probability was that we had some information about theta and how. So again is
So you can just alpha is getting more ancillars and put this otherwise.
yes. So the point is yeah. So alpha has not changed in all of this. Alpha was tensored with all of this. Alpha just remains alpha, completely unentangled with whatever I was doing here. So I don't even need to do this measurement. I can just like do more copies of the circuit. So like I can just do this like so. This is what I was saying. You can have another one here. Put H here. Okay. And goes like here. And here I again put a U. And then again and then measure. Like at the end, all measurements at the end. Similarly, I can have as many as I want. I can have some T of it.
So eventually you want to measure all zeros. like the separation from all zeros, you have amplified.
Yeah, so no, you not just count zeros. Count the number of zeros. So we do the measurement and count how many zeros we got. That's it. So and yeah, so now
You get a good rational approximation to.
yeah, so let's see what we get for this. For this one will not give us a very good approximation. But yeah. I mean, it will give us something. To get to good approximation of this will require too much. So then we have to do something else. But let's just see. So this construction is clear, right? So you put many wires. So how many copies? So okay. So suppose I put T of these zeros. How many copies of U will I have these? T of them, right? So then I see, right? And what is going to happen is, so after the first one, all the other two bits are where? What is the state of them? So
After the first one, they are all still zero.
they are also zeros. And then this and alpha just stay there. And so then we start acting on one more of them. And so at the end, the whole thing looks like what? So the whole thing, so the final state looks like,
The tensor power.
yeah, it's a tensor product of the same vector. So that's like the quantum analog of of independent samples. So the final state looks like a tensor product of I, so which is like tensor power, or T of this is exactly the same thing. So this, by the way, what is this? So I only did one of the right. So the one thing also has the written now. So, but it's size. Huh?
This one was passed by 3 by size.
Yeah. So 1 plus x I theta by 2 0 plus 1 minus x. So and then alpha is tensor of the dots. So this is the final state. And now if I measure, so yeah, so if I measure all the so if I measure all these qubits, so what is the distribution? Yeah, it's independent Bernoulli. Okay. So if I measure, if we now measure all the qubits, their distribution is the product of Bernoulli of this 1 plus cosine theta by 2. Actually 1 minus cosine theta by 2 because so that just means that there are t bits I'm going to get, each is all of them are independent, and each one of them the probability of getting one minus. So that's the so now what? At this point. Yeah, if you count the number of ones, or yeah, count the number of ones, and so you basically get that. So by so-called Chernow bound, probability that number of measurements equal to 1. So number of measurements equals 1. That minus 1 minus cosine theta by 2 is less than equal to delta, is less than how much? Yeah, there's some cosine theta dependence also, but let's forget about that. And it's at least e power minus 2 times n t squared is bigger. What does t? Yeah, it's like memory issues. Yeah. Okay. Okay. So right. So but this is this is as good as getting a relative approximation or delta like the delta here. Okay, so this is as good as getting a delta. So so this whatever, so this gives a delta. So after t steps, we get a delta by 2 approximation with this much probability. So, if we do t times, then and we put the parameter as delta, and the probability of error is minus t delta squared, and exponential is minus t delta squared, and the approximation of cosine theta is up to delta. Additive error delta. Okay, so but we have to find theta, right? So what we do? So t we will leave open for now. So t is in our control, right? So there are two parameters in our control, delta and t. Delta is how much growth we want to get, and t governs what will be the probability of error. So yeah, so but this only gives us cosine theta. To get theta, what else we want?
No measurements divided by t, right?
No, this is
Yes.
oh yeah. Here it's a fraction. Divide by two. Yeah. Right. Actually, I don't even need to do this by 2 here. It'll actually be very stronger. But yeah, that's very important. So yeah, so now so we want to get theta, right? So this says that t with t measurements we get a plus minus delta approx to cosine theta with probability at least 1 minus 2 times x puff minus t delta squared. Okay, so there are two things now. One is to see what is the predominant error, but before that we have to do one more thing. Let us do that first. So we got only cosine theta. We want to get also sine theta. Or is that enough? So like how to get angle, what all we need? Like if we know cosine theta, what else? Is knowing sine theta and cosine theta enough to fit down an angle? Yes, because that brings down the vector on set. So if we get sine theta also, we'll be done. So how should we get sine theta? Is there a similar circuit? So let's just look at that circuit again. So here there is e to the I theta.
We can estimate theta plus
Pi 2, right? So what is pi by 2? I. If I could multiply by an I here also, I would be fine. Right? So how do we multiply by I only on the one side? Yeah, just apply the phase gauge. So on the top qubit, between the two Hadamard's somewhere, also apply the phase. Actually, after that, yeah, between the two Hadamard's, apply the phase gauge. So the one thing gets a factor of I in, then you acts, and then you. So to get sine theta,
The first time we're applying this gate, or
sorry,
this is the first time we're applying this gate, or we applied this phase gate before?
so phase gate we saw it, I1,
No, we saw it, but will we do it in any? This is the poly Y gate, no?
no, it's not polygon, this is simpler, one I, this is the
This is the one I.
this is the square root of z,
One.
yeah, this is the simplest. So yeah, so we also want sine. So consider.
So the one I.
we need to
And now the same argument gives us that the final state that 0 alpha maps to 1 plus I x I theta by 2. 0 plus 1 minus I. So 0 is yeah, so 1 so it's the cosine square is 1 plus 1 plus the cos of pi by 2 is 1 minus sin. Yeah.
We have some additional information about it's rational.
No, nothing. Nothing. Right now, so far we have never seen how close can we get just by this procedure. Then we'll see how to come. So then the same thing. I mean, this circuit can be run in series with the other one. So again, add more and more things. So add t of these guys also. Right? So now you have a total of 2t. Right? So add t of these rounds also. So finally, a very probability 1 greater than. So what is the error probability? Both of them will have some error probability of 2 times, right? So the error probability adds up. So the probability greater than 1 minus 4 times x minus 3 delta square by 4. We have cosine theta and sine theta of this plus minus delta. Okay. So what does that tell us about theta? How much error do we have in theta? So this is the correct point. Let's say.
So on both sides, right?
So we have some point which is like whatever, like delta in infinity now, right? In each direction, that's more delta, sorry, right? So yeah, so you can think of it as a square. So there is a correct point and there is a square of side length 2 delta, where our estimate lies. Okay, so what should we do now? So find the closest, so the easiest is to find the closest point of the edge. And then what will be the error? Like, so the closest point in Euclidean distance, right? So at this point, so let's call these things there, let's keep this name. So let U1, U2 be our estimates. Your estimates. Cos theta sin theta. Then U1, U2 minus U1, U2 minus the correct thing. Cosine theta. And if V1, V2 is the closest point on the unit circle, V1, V2. I mean, I'm doing close point. You can do almost anything and it will work. Anything you can do it will work. Close point is the easiest one. Close point is the circle, so then what can I say about that? It's also less than delta variable. Why? Because cosine theta is also a point of itself. So V1 V2 is closer than that. So if that distance is less than W2, this one is also less than W2. So now I claim that V1 by V1 V2 is in Euclidean distance quite close to cosine theta sin theta, right? So let's slightly. Sorry. Yeah, that's triangle inequality. This said that so this means that V1 V2 minus cosine theta sin theta divided by. And now it's okay. Like I mean, so I've only managed to bound the distance. If the distance is small enough, angles will also be small enough. So let's say that we can choose delta some constant such that we will be able to, let's say, get theta within error of pi by 8. By error of pi by 8, I mean that in that arc, the theta will be, so we will get some point and we draw the arc pi by 8 on both sides. Yeah, pi by 8 on both sides. Then my correct angle will be contained. Or let's say we can move, so let's say pi by 16 or so. So if we draw the arc pi by 16 on both sides of the angle. So there's some constant here, so it's there. So we can choose some fixed constant. Delta, no, delta, if delta equal to delta naught, or delta is less than equal to delta naught. Then we can obtain so we can obtain a yeah, so that is okay, so that we can obtain plus minus pi by 16 approximation of theta. In this, I mean, angle there is a wrap around it. So my notion of approximation is that if I take the actual angles and take whatever my measured value is and draw the arc of pi by 16 in each direction, then theta lies there with probability at least 1 minus 4 x minus t delta naught. So this means that theta lies in the arc theta at minus 5x plus 5x. And these are all mod 2pi. So we are the angles. So things are that. So all distances are. So for example, 0 and 2pi are supposed to be very close. That's yeah. Okay. So yeah. So good. So but okay. So now let's start worrying about. So is so far everything clear. So we choose some constant data. That's the important point. Fixed constant. It does not depend on anything in our problem. Not on the number of qubits. Nothing. It's some fixed number. It's like it's going to be like 1 by n to the 1 by 40 or something. And you can actually calculate it in algebra. So that we will get this whole process that we have described so far will give us theta up to plus minus pi by 16 error in this sense that if the arc there will be some point, and if I draw the pi by 16 arc, then theta will be there. And this will all happen with probability. So this event that theta lies there will happen in with probability at least 1 minus 4 times x pop minus t delta squared. So one thing to check here is just to call what is random here? Is theta random or theta random? theta hat is a random variable. That's what some people don't measure. Okay. So good. So now everything's fine. Okay. So now let's start thinking about T. So what is the size of our circuit for doing all this?
T times the size of U.
Yeah, so T times the size of Q plus T times T many ancillas, 2T many Hadamard's, and T many K. Okay, so it's all order T.
So T is again frequency, just a constant, the kind of error.
Yeah, so right now, yeah, we don't know, but any
So the parameter here
is delta. So yeah. So right now with constant, yeah. So by taking T to a constant, I can get it as constant error. If I want, but suppose I want my errors to be very small, like I don't know. So like maybe I have n qubits, and I want the error to be like poly 1/n. So one over poly n. Then how big do I have to choose? How big does T have to be? No, sorry. Login is enough. So yeah, that will be important. So now if I want 1 over exponential T, huh? So if I want exponentially small probabilities, there are probability to be exponential into like 2 to the like 2 to the minus n and volume. So the dependence on T is very nice, basically. Like the dependence on delta is not so much. Right? So the dependence on error probability is very nice. Not the T. Dependence on error probability is very nice. Depends on Q and error probability. Depends on T on delta is not so nice. T has to be about 1 over delta squared, whatever, if I want to start at least that. So what can we do so far? In polynomial, so in whatever the size of U is, some polynomial factor of that, we can get constant like approximation, like pi plus pi by 16 with extremely high probability. 1 minus something inverse exponential. So that's the so far. So we can obtain plus minus pi by 16 as approx theta in time in middle circuit with size poly and where n is the number of qubits. In fact, it's not even polynomial, it's like much simpler. Um, in time with probability greater than 1 minus x poly. But the point is okay. So now let's just keep our goal in mind. Our goal was factoring. Factoring, in fact, wanted us to do exact order estimation. So delta has had to be essentially 0. Of course, that we can't do, but there we know that the order is some nice thing, some rational number. So we can potentially, if you have very good approximation, we could just say, okay, only some rational numbers of this kind lie here, and we can just zero it. But anyway, even that will require some at least how much approximation. So at least the following is the kind of things you were looking at was on K by R. R was the order. Order could be potentially linear in N. N capital N, which was like 2 to the N, like smaller than the number of qubits, which would be log of the big number N. So delta would have to be of the order of 1 over big N, exponentially small. But that will, in this thing, will require T to be exponentially large, right? So, but if you want, yeah. So this is not good enough for our purposes yet. But for the factoring application, this approach so far would require delta to be about 1 over n. In fact, it will require it to be 1 over n squared. Where n is equal to on. So, which will force P to be responded. Let me is a super column. So this, of course, this is not. So let's stop here and let's make it. So this is good in the sense that, well, it's giving us some constant approximation with any, like almost any probability, any as good a probability one. But our application requires very high precision. Also very high probability, very low probability, but also very high precision. Right now we only have constant precision. So now we want to improve this precision. So my claim is that at this point there is actually a very simple way to do it. So remember we have some black box, sorry, white box that we can play with you. So maybe we have access to not just U but other things also. So suppose we also have access to U squared. What will this whole approach do to U squared? It will give us a plus minus pi by 16 approximation to Q3. And then yeah, is that correct? Because these are not numbers, these are angles. Like, not be slightly careful. So if I say 2 theta is equal to 90 degrees, I can't say theta is 45 degrees. It would
So it could be 45 degree or it could be like.
yeah, or it could be like 235 degree also. Is it 235? 225 degrees. So yeah, so then what? Yeah, that is all we can do. So we will just somehow. Can those two solutions be very close? That's the first question. So suppose I know that 2 theta is, so if 2 theta is a particular value, there are potentially many solutions for theta. Actually, there are only 2 solutions for theta. How far are those 2 solutions? 5. So they're at least 5 apart. So then what?
Just
So let us recap what we have. We have a pi by plus minus pi by 16 approximation for theta. We have a plus minus pi by 16 approximation for 2 theta. And we know that there are 2 possible solutions, theta for theta given 2 theta. But there are at least 5. They are exactly 5 for
Transformation to theta to.
yeah. So the point is that the fact that we know the approximation to theta up to plus minus pi by 16 and the 2 solutions are at least pi apart means that we can fix the correct one. So like there are, so if I have 2 theta, I divide it by 2, I get 2 different things, but one of them is the correct one because that's the only one that lies in the correct range. And that is now what? It's a yes, a pi by 32 approximation of theta. Okay, so now what? Yeah, so yeah, and this is actually the recursion is quite present. So it's like so you get a pi plus minus pi by 16 approximation to everything to u squared, u to the 4, u to the 8, u to the 16. But there's something else also going on here. But let's just worry about that later. U to 16, U to 32, 64, 70. The powers of U to the powers of 2. The right return. And each one you get a plus minus 5 by 16 approximation. But the point is that at every level, you have a plus minus 5 by 16 approximation here and some delta approximation here, which is very because so there's a final case and there's plus minus 5 by 16 approximation, and on the higher level, there's a delta approximation. Tells you a delta by 2 approximation at this level. And then the induction goes through. At the last level, if you do this L times, you get a 5 by 16 by 2 to the L approximation. Now everything is fine. How many rounds of this will have to we have to do to get to our 1 over n squared capital N squared kind of thing? Sorry? Order log capital N, which is which is about n, so small n. So still everything is column. Is everything column?
Number of views that you use.
Number of views use exponential if you could not somehow do faster exponentiation of you. So now we are doing one more thing that somehow every power of you, every power of every like we can do repeated squaring on you somehow. That u to this u square, u 4 to 4, all the way up to u to the like all these. So there are like small n numbers, pieces, u to the power 2 to the n. All of these we are doing can be implemented in for poly n size. This is not like an outlandish thing to think, but it is not because our application is was what factoring, and for factoring, what was u? U was multiplying by a, some fixed number a, classical number. So the basic vector corresponding to x went to ax modulo n. This is a very classical, this is a classical operation, and then whatever you convert the classical circuit point. That was what we were going on. But so what is u to the power whatever n u to the power k for n k? It's multiplied by e to the k. But there on the classical side, you can do it fast exponentiation. So you just compute it with a classically, the circuit of that will also. So this is all because everything is happening modulo n. So all of these will be capital, like small n bit numbers. So all of these seem to have possibly very different circuits, but all of size poly small n. So you have poly small n circuits, poly n of them, and this will essentially, so you are going to use T to be, so T will have to be quite large, like large enough polynomial in n. Actually not in polynomial, just large enough logarithm, like large enough multiple of the log of small n to kill off this polynomial in n many errors. So this is the input. And then at this point, you will have done phase estimation. You have the phase to 1 over 2 to the 2n or 2 to the 4n or 2 to the 8n, whichever you want, additive precision with very high power. So that's the structure. Still, does it solve factoring? Sorry? Yeah, no, you also need the eigenvector. So in the factoring case, we don't, because the eigenvector itself was like crazy. So that will come to, but let's just write down this intuition, whatever I was saying. But are there any questions at the high level? We see another big version of doing this via something called so this can be over thought of as something called quantum Fourier transform that we'll see in the next class. But this basic version is fine. So still there are many things to do for factoring, which is one is the classical part to do rational recognition. But even before that, there's a bigger problem that we don't have the eigen. So but that actually is a very nice thing. But but until now it's everything gets. And so let's just write all this down. And slowly. So, yes, so now. Next. This is the argument that we did. Basically, 2 theta mod 2 pi has two solutions to theta mod phi. And because of the pi plus minus pi basis percent, only one of them. And that one will be a epsilon by 2 approximation. Okay. So, okay. So then again, right. This probably is 1 minus 4n plus 1 or that and 4n come and like. Right. Plus minus 1 over 4 5. So the total circuit size. So we can set C to be some whatever 1 by delta where under okay, circuit size of um, order NP plus
n times max circuit size, this is probably one minus one equal. Yeah, actually, we gave it just. Okay. So yeah, circuit size is nicely polynomial in small n and we get good approximation uh, and okay, one more thing that the circuit does, what does it do at the end? So what does this whole circuit look like? So basically it looks like plus the circuit looks like this. This is alpha, right? And there is U happening and all these things are happening here. And some other things are happening here. With all these gates here. It's a controlling also. But the output zero, like all zeros, alpha, and how many zeros? Some whatever, so like 4 and 0, something, 8 and 0, something. So all the zeros. This maps a bunch of products, like it's a bunch of tensors. So it's a bunch of tensors that you can have. And on the ith guy, there is some particular probability pi or something like some square root of some alpha I. One. And this whole thing is censored with that. This is the thing that is happening on the. And then we are going and measuring all these qubits. They're all independent completely. All these measurements and basically doing classical stuff. And alpha is still remaining there. Okay. So this alpha I, this okay. So maybe let me not call it alpha I. Let me just write down. So let me call this SI alpha. This will become important very quickly. T alpha. So this, of course, these numbers depend upon what alpha was. They depend upon actually theta. So these. Okay. So and yeah, depending upon which U it is and whether we are using a K or not, they have different values. But all of those values can be written. Okay. So is this so far? Okay. So no questions. So we can then go back to factoring. Yeah, I thought that I will not get beyond this, but when you finish factoring, would except for the 20 factoring.
So after you measure, you still need to change the quantifiers.
So to what?
And you want it, these are ancillary, so you want.
No. Okay. So ancillary, all of that is only before like in the middle. Once you measure, it's okay. Right. Yeah. So anyway, at that point, all bets are off. So yeah. So the things you measure, you don't have to change that. Okay. So this is the circuit. The thing, if alpha was there, we can do phase estimation.
So now let's try to go back to our factoring problem and see what this means there. Just remember this expression. Expression is 0 to alpha. Start with all the answers and whatever, all the workspace bits in 0 alpha. Is insert it, and then it goes to this product of bits with like nice biases. All the biases depend upon alpha, and then alpha is nice fictions. That's right. Okay. So now let's go look at the factoring again. So in factoring, the unitary we had was the following kind. So the problem we were trying to solve is to find the order of A modulo n. Capital N was some big number with small n bits. So capital N is not 2 to the n. It's some number between 2 to the 2 to the n minus 1 and 2 to the power n. It requires n bits. Small n bits, and we are trying to factor it, and we saw that classically it can reduce to something called order kind. So you find number A. A is between also 1 and n, it's co-prime to n, and you want to find the order of A modulo n, which means it's the smallest number t, positive number t, so that A to the power t is 1 modulo n. That's the order. And that's what you want to find. And here was the idea that you look at this unitary. Okay, what is this unitary? It's only described in the classical. So you think instead of ei, just think of it as get I. Okay. So on get I, it just acts for identity if I is not co-prime to n. That's the first thing. If it is co-prime to n, it multiplies it by 8. Okay. This is unitary because why? Yeah, because A is co-prime to. That's the important thing. So because of this, then for some part of permutation, the remaining is a permutation. For part of the identity and the remaining is it's a unit. Okay, it's a unit. And then this was what we wanted to do. There are many eigenvectors of it, which we could write down, sort of like Fourier transform this. So you take any number k between 0 to r minus 1. R is the order of it. This is the thing we want to find. We don't know this. R is the order. And UK is just, so one of this is a normalization. And what you do is you look at e to the a to the j model. So a to the j model, that the ket of that, that's what it's. That's some number between 0 to n minus 1. And the corresponding coefficient is e to the 2i by kj by r. So the k, this k is this j is the sum. Okay. So by the way, what happens in k equal to 0? What do we get?
One on the.
Exponential.
Sorry? Exponential.
So you just get,
Yeah, this is 1. So you get the usual uniform superposition of all the e to the a's, j going from. So basically, if you think of it, it's like the subgroup generated by A. It's just the indicator, the quantum indicator of that. That's what it is. But for each element, there is a corresponding ket, and you just take the uniform superposition. That's what it's. So that's the k equal to 0. Okay, good. Then we also saw, it's so easy to see actually, that each of these is actually an eigenvector of U. It makes sense because the point is, what will you do on this? So what does you do on these ways? It just takes j to j plus 1, right? And what does j plus 1 mean? J plus 1 is also modulo r. So up till r minus 1, r minus 1 goes to 0. So it just like rotates. So then it's easy to see after that this will, because it's rotating like this is linear, so this thing will just come out here. This is a simple algebra aside, and it's the geometric picture. Then the corresponding eigenvalue is e to the r 2 by k by r. So UK as K. Okay. So if we had our hands on any of these UKs, we could get K by R. R is what we want. And if we need K also, it will be done. But it seems hard, right? I mean, this thing itself seems to require the knowledge of K. Okay, good. So now what should we do? So what is the uniform superposition of these UKs? So that's or maybe even before that, are these UKs orthogonal? Why? U is not Hermitian. Eigen values with the same not your problem. But here there's one.
So we can get UK, let's say UK times U.
This is actually the discrete Fourier transform. So same reason. So it's just yeah. So because basically you're thinking you're taking e to the power 2i pi by r. That's a primitive root of unity, and looking at omega to the kj. That's the vector. And the other one. So if you look at UL, that will be omega to the lj. When you take inner products, it will be k minus l, because inner product, remember, one of them will conjugate. It will be k minus lj sum. And if k minus l is anything that is not zero, this will cancel out. And if it is zero, so then it will be 1. So these are orthonormal vectors. What is their sum?
It's EA.
Sorry?
No, it's just one.
E1, yeah, so it's a get 1. Yeah. Because again, for the same reason, all the others are sums of various, like, some, like, all the powers of a particular root of unities. They all cancel. Only thing that will remain is the big first one, which will be the 1 vector. So, I mean, of course, after normalization. So, what is the uniform superposition of the UKs? Yeah, the uniform superposition of the UKs is just E1. The vector corresponding to the number 1. That we can consider. From 0, we just, I mean, the simplest way is just think of the unity operation which adds 1 modulo n, where we know. Or, yeah, right? So 0, so you start with 0, you go to 1. But this is not an eigenvector, it's just uniform superposition of all the eigenvectors. Okay. So now what? So suppose we run our algorithm, what will happen? So now let's go back to this picture. So far what we have done, we have seen that the get 1, just the number 1. So all 0 and in the end 1. Correspond to integer 1 is a uniform superposition of all these eigenvectors. Is that clear to everyone? We'll write it down, but as at least intuitively is it clear apart from the algebra. The reason is basically the fact that things here are powers of roots of unity. So basically for the same reason that Fourier transforms like orthogonal, you get all these things. Okay. So the vector get 1, which we can construct, start from 0, just add 1. This is a reversible operation. I mean, like add 1 modulo. So this you can go from 0 to. So we can construct now something which is a uniform superposition of all the eigenvectors. The suggestion is that we feed this in place of our alpha in this set. Okay, instead of alpha now, we have a superposition of like uniform superposition of different eigenvectors with different eigenvectors. Okay. But it's a uniform superposition. That means okay, what happens here?
Summation over alpha.
Yeah, so now so by linearity, what you have is so the same superposition happens here also, except that corresponding to alpha I, whatever, corresponding to the eigenvector ui here, there is these numbers depend upon that particular ui.
SINTI.
Sorry?
SINTI would be.
Yes. So now, okay, so now let's suppose we did the same process as before. What is going to happen? So remember, the state is, it's like, so let's suppose it's a case of two things. Suppose there are two eigenvectors, orthogonal, alpha and beta. Alpha, beta. Okay. So that instead of alpha, okay, alpha plus beta by root. And alpha and beta are orthogonal, remember, orthogonal eigen. Unitary eigenvalue vectors need not, they need not go to. But yeah, but here they are orthogonal. So alpha beta alpha will dimension, alpha will beta by root 2. Okay. So there will be this SI beta. So the number of these qubits will also be the same. So SI beta, GI beta alpha plus. So the 1 by root 2 here plus 1 by root 2 SI alpha. Sorry, SI alpha is this into alpha by root 2 plus 1 by root 2 SI beta around this beta. Okay. So that's the situation. That's the thing. In this, we do the same thing that we are doing. Exactly the same process. Measure those qubits now. What is happening? What is the distribution of the measurements I'm making?
Either you get alpha on the.
No, but alpha we are not measuring. Those things we never measure.
So yeah, you will get either you get the SI of alpha and stuff. In the right and the bottom part, the one will end up, which you will end up in state alpha, or you will get SI of beta and the.
No, but let's just think. So there are many ways to think of it. Maybe the crudest and simplest, but it will always work. Is suppose I just expand all these out. So basically, I have huge bit strings, right? I have this thing over bit strings. So there is like all of them are like they look like this superposition of all bit strings with different weights. So one of them is weighted by alpha, another is weighted by beta. Right? Some function which is dependent upon some. So this is like all the measurements I'm making, I'm putting it there. So there is some f of alpha and the x, the whatever the measurement m. So summation over all m, f of alpha n, get m. M is this whole bit string. Sum over all times alpha divided by 2 plus sum over all m again, f of beta n times beta. But this I cannot write at get m, because this is what I am measuring. Get m into f of alpha m by 2. F of alpha m root alpha, f of alpha m get alpha plus f of beta m get beta by root 2. And so on. For each m. So now you see. So basically, what is the probability of measuring a particular thing? The length, the projection, like the length of the projections. The length of projection is around length of whatever this coefficient is. Which is what? Because alpha and beta are orthogonal. It is f of alpha m squared by 2 plus f of alpha beta m squared by 2. It's just a mixture. If the probability was f of alpha beta there, f of the coefficient was f of alpha beta there, the probability was f of alpha n there. Probability was f of alpha n squared, whatever actual value squared. Now the probability is f of alpha n squared by 2 plus f of beta n squared by 2. It's just a mixture. And what is the 2 coming from? Because it was a uniform mixture of alpha and beta. If it was some other mixture, let's say 0.8 root alpha plus 0.6 beta, which is we square some square and so on to 1, then those things will show up. It will be like 0.64 for alpha and 0.36 for beta. Right? So the same thing will of course work in the K team also. And so then what is happening is a uniform mixture of all the probabilities. So essentially what is going on is that we are seeing, like we can think of it like this, that one of the eigenvectors is essentially being chosen at random, uniformly, because of uniform superposition, and they're getting the answer corresponding to that. That's the bit string we saw. That's the distribution of the bit string we see. And therefore that's the distribution of our answer. After that, our algorithm is determined. So whatever answer we are getting is a approximation to k by r for a uniformly random k. So is that we will do so we'll come back, keep coming back to this example. This also motivates something called reduced density matrices, which makes just whatever I was saying this right now it's sort of in a I mean everything I said is actually completely regular because there was no hand label. but it makes it more convenient to see. But let's again go through it. I'll write this down. But the point is that here you're not measuring alpha ever, but still, basically what is going on is that you're somehow ignoring alpha. And because you're ignoring alpha, the way it comes to the picture that your state on these things does not look anymore like a quantum state, it's like a probability distribution over quantum states. And that's the notion of a reduced density matrix. We'll come to that later. But you can also do it by hand, which is what we were just doing. Just expand this whole thing out Right? So these are all the qubits, all the classical bits you are seeing, just expand out in the measurement basis. And then you have different coefficients for different alpha, these alpha are common. So now for each measurement basis, look at what is the coefficient. Coefficient something in alpha and beta. When I measure that, I'll get something which is the length of that vector. And the length of that vector is just a mixture, just the average of the lengths for alpha and beta. And the average weights are exactly the weights of alpha and beta in the initial superposition. So in our original example, the weights are all uniform, 1 over k, 1 over root k, so square 1 over k. So we will get, so the bits, the distribution of bits we are seeing is no more independent. It's a mixture, it's a mixture of independence. Just like it looks like that one of the k is to the uniform random, and then we get the answer for that particular distribution. This is not what is happening. I mean, it looks, the process looks somewhat different. The distribution it produces the same. Distribution looks like just a mixture. It's like just a convex combination of independent bits with different weights. And that mixture is that probability 1 by k is the independent distribution corresponding to P1, the probability 1 by k is either 1 corresponding to P2, and so on. So the final answer you get, the distribution of that is probability 1 by k is the answer corresponding to k by r, which is just a pi plus minus pi by 2 to the 4n plus 4 approximation to k by r. So in the end of all of this, what we will get is not k by r, but a pretty good approximation. So r is at most capital N, right? And we are getting something like a 1 over n before approximation. And we don't even get 1 over 2 n squared. So, and this is let's say at this point we hit it with a hammer from the theory of scientific fractions that if you have a rational number whose denominator, so the denominator is what we're trying to find. You have a rational number whose denominator is at most t, and in the so denominator is at most t, and you get a approximation to it that is at least 1 by 2t squared, some other rational approximation. Then you can find the correct rational number. It's just by doing something called like a continued fraction expansion of the approximation efficient. So we do this. It's a nice thing to know. It's a nice very many applications. It's a non-trivial thing. It's highly non-trivial. I mean, one can imagine, oh, I knew n and it just search, right? But you don't know n. So it could be that the grading is 1 over n, or 1 over n minus 1, or 1 over n minus 2, or 1 over n minus 3. All these are somewhat different. And the country parameter, don't worry about that. As long as you have a good approximation, all you have to know is that the grading is not too fine. The denominator is at most n. And you have an approximation that is slightly better, 1 over 2 n squared. Then you can find the exact answer immediately. So the obvious thing that one can do is that if I have denominator is n, and if I have something, an approximation that is better than 1 over n, then I can find the exact. Or maybe 1 by 2n, then I can find the exact. Just by, like, it is an opinion, but it's not an opinion, it's much more. So we will do that also. So yeah, that will be a complete classical. There's nothing point about that. So yeah, so but is the general strategy now here? So then okay, after that you have basically your uniformly random k by r exact. And so from that to find out r is easy, that argument you already outlined. This is the point that you keep sampling k by r uniformly random. The only reason you will not hit r, so what will you do again? You will take k by r, but of course you will not see k by r, you will reduce fraction. It will not have r, but it will be some divisor of r. So the only reason you will not get r by taking LCM of these things is because some prime factor is always appearing in this kn. But for any prime t, the probability that it divides k, because k was uniformly random will be 1 by p roughly. So if you do enough trials, each prime t will at some point have not hit, and therefore you get it. So all of these are easy classical exercises. So the tricky thing is one of the tricky things. Of course, phase estimation itself is a pretty not amazing thing. But the other one is that even phase estimation is not enough because for the eigenvector, then you notice that you don't have the eigenvector, so you have only forms of the position of an eigenvector, and that is what. Okay, so is the general strategy again? Just slightly down. Not 10 minutes. Okay, so now we revisit. We want to give zero. With eigenvalues. It's like this one. It's I. For unknown R, it is interesting. With the following properties. Orthonormal. And get one is equal to 1 So then we run the algorithm. And of course set to 1. And this we can do because we start with the algorithm here is converted to 1 that we the expression on the previous slide. Place that we get in each run of the algorithm. Plus minus 5 by this 2 to the power whatever 4n approximation of 2 by k by r for a uniformly. In each run, there's a uniformly random here. So uniformly random. Yes. So with this probability, so the algorithm succeeds, and if the algorithm succeeds, you get this. So basically, here you say that we just like, I mean, so these are easy to check whether you have succeeded or not. Right? So you will assume the algorithm always succeeds, because then if you are not able to factor using the order that you found, then you know that you failed. So you run the whole. So it's easy to check, and even if you succeed by accident, it's good because you have factored. So it's not yet. But anyway, so yeah, so this, but yeah, it's a bit of a weird statement because there's some inherent randomness in the algorithm or the process, which just chooses one k at random and gives you the answer. The probability is not about that random, the probability is about the other random. And so if it succeeds, then what you have is a uniform random sample from these approximate numbers. That's the setup. And then from this, yeah, so you say that if the algorithm has succeeded, then I have some k by r. I don't know what k, what r, but all of this I can, but k by r I can at least get all of this by doing this rational number.
And then the various arts that you get,
Yeah.
that you take in this.
Yes, yes. So that's the input. So you get all these. So you get K by R. Of course, you don't see K and R. It will become reduced fraction, K prime R, right? So basically now you take many of these and you take the LCM. Why will that not? So all of these are divided apart. The LCM cannot be more than. Why will it not be R? Because it will not be R only if there is some prime P that somehow you got so unlucky that for every K that you got, it was dividing that K. Only then you will not get R. But the probability for any one K that the prime P does not divide it is like 1 by P. So the prime P divides it is about 1 by P. So if I do it like L times, the probability is 1 by P L. And there are at most log L of these primes. So yeah, so the whole length, actually you can take a unit one over all the primes. So summation 1 over P by L, which is itself can make it as small as you want. So yeah, so this can be easy. This is right in the right. Yeah, the simplest thing I think is that to take 1 by P L, like take L to be large, P is at least 2, so you take L to be say like L to be about N or something, and then or 4N or something. So then this probability of for any one prime becomes like 1 over 4N or 1 over N cubed or something. And there are only about smaller such primes because log. So the whole thing is 1 over all these.
Because we can check.
Yeah.
I mean, there's a reasonable chance that for one of these random choices.
Yeah, I think the correct thing.
You'll
Yeah.
actually get it.
Yeah.
Because K will be prime and not a prime is an.
Yeah, and then you understand. Yeah, so in principle, you could just do this. Whichever R prime you're getting as now, just to try it out, and that's the order, and run the rest of the process. If you succeed, you're done. Yeah, but even then, even otherwise, it's